Okay, everybody able to see this white screen?
Yes, sir.
Okay, good. Uh, Today in particular, we will discuss two or three different algorithms. Okay, one is what is called a gift wrapping, and second one is quick file. Okay, these two we'll discuss today. And see, if you look at this previous algorithm where we are finding the extreme edges, okay, and we slightly modify that. So idea here is, if you find a one extreme edge and use that edge as an anchor edge to find the next edge. See, for example, uh, suppose if you have some points here in two-dimensional plane, and somehow we found a one edge. That could be any one edge on the convexal of these points, and use this edge as anchor to find the next edge in the sequence. So here the convexal is like this. So if you know this edge, find the next one. Okay. Similarly, use this edge, find the next one, and so on. Okay. So that actually we can find these extreme edges one after the other in the order. Okay. Uh, Now we are discussing about counterclockwise order. Okay. So that, okay, we can report them in order. So this is the what is the idea here. Okay. So how this works? Let's see. Yeah, maybe we can take the same example here. Okay, take out this. Yeah. So now we know that this is the what is given to us. One starting anchorage, something is there. So if you look at, if you want to find out the next one, that is this edge. So how we can do it? Just if you look at this edge, if you extend this edge, and if you try to connect all of them here to this one, and the if you measure this angle, okay, this angle is the smallest for this vertex. Okay, so we use this property. Of course, this is not a I mean trivial one actually, but if you look at this one, this line here, okay, so all the points are one side of this off plane. That means this edge is part of the convexer. So this property, whatever we discussed in the yesterday's class, we're using that property. But here, for a computation point of view, we can measure this angle to identify this vertex. Okay. So from one edge, how we can find out the next edge? You find out these angles, all these angles. And one which makes the least angle, that is the next vertex or next edge. That vertex defines the next edge, next extreme edge in in counterclockwise direction from the uh, anchor edge. Okay, so how much time is required to find this one? So since there are n points are there, you have to find out this all these n angles. Okay, uh, basically if you don't count this one or this one, okay, and you have to consider all the remaining n minus 2 points, you have to find these n minus 2 angles. So each angle can be computed in constant time. So finding all this angle takes a linear time, and taking the minimum actually it takes a linear time. So in linear time you can find out the next stage. And worst case, all the vertices may be on the convex hull. That means there can be at most odd and extreme edges. So we have to repeat this for each and every edge. So worst case time complexity is basically odd and square. Okay, is this clear? This is what is called a gift wrapping. Any questions here? So this is called a gift wrapping because when you are wrapping any gift with a gift wrapping paper, okay, we put it on the table and you put your gift and you wrap around it. So the way you are wrapping around it, okay, finding the next edge actually that's okay. This process of finding the next edge actually simulates the gift wrapping. So that's why this name is given. So now only issue is how to find out the first anchor edge. Uh, can you think of some way of finding this first anchor edge?
So we can use the leftmost point.
Okay, leftmost point is this one. How we can use this one?
Sir, like it should be definitely there in the boundary because it is the extreme
Yeah,
point and every
yeah, that is
point.
true. We need a extreme edge, not a extreme vertex. So we are anchoring this with respect to some edge. We are finding the next one with respect to a previous edge. So we need a one edge. So one point is not sufficient.
And for this point, we can run a loop and check whether all the points are uh, same side of the line to this edge.
No, we are start. You said that actually we start with this particular vertex. Okay. So how we can actually find the edge actually from this vertex?
Now, for like we have to iterate through all other points and check for that particular point whether we are having all other points on same side or not.
For this, we can use the y-axis to minimize the angle.
Yeah, that is true. So, okay. Here, what we do actually when you find this one and you take a vertical line here and use this as a anchor edge and find out the next one. Okay. So similarly here also, since we started with this one, you take the bottommost vertex and take a horizontal line passing through this one as a anchor edge. Okay. And with respect to that, you find out this edge, which makes the smaller angle. So keep on doing this one. So this way we can, of course, we can start with respect to any vertex which is on the boundary, but we have to choose appropriate line segment so that actually all other are actually one side. So this can be done easily. If you have bottommost point, then you can take a horizontal line pass through that one. Then if you're taking leftmost one, you take a vertical line pass to y direction. Okay, line and just do that one. So this is the way. Is that clear?
Sir, will this also work in more than two dimensions?
Uh,
Sir, I think there we have to choose planes instead of lines.
yeah, you can do the anchor plane actually. That is true. Okay. Yeah, gift wrapping can be extended to this. Okay, 3D also. Yes, possible. Yes. So here, what we have to do actually is here you have to anchor this problem with respect to some triangle where these 3 points are actually on the boundary of this one. Okay. Now you take any one particular edge, okay, and find out this next edge with respect to this one. Okay. So that okay, the same idea can be extended. Okay, but we have to see. So basically, we are doing this search in this direction, and maybe if you maybe need to backtrack and you have to search in this direction also. So if you're able to visualize in 3D, then you can able to. Okay, maybe I'll switch on this video so that actually I can tell. Okay, maybe I'll go back to this. Okay, so here basically in 3D, what happens actually, you will have a one plane. Okay, anchor plane. Okay, all the points are above this. So you have a triangle on this plane. So you have to, if you're having a gift wrapping paper on the plane here, and you have to try to rotate this one on one of the edge. So in the 2D case, you are rotating this paper gift wrapping on one vertex, so that whichever it's the next one that we are taking. So that we are identifying with the smallest angle. In the case of 3D, you have an anchor plane on which you have a triangle here. On this plane, we have a triangle here. Okay, and you take one of the edge and you rotate this gift wrapping paper so that till it touches another edge. Okay, so you have to take a one edge and you have to see with that edge which vertex makes the least angle, and you have to identify that one. Okay, you are able
Sir,
to visualize.
yes, sir. Sir, but in 2D, finding the bottommost point is easy, but in 3D, how do we find the bottommost point?
See, in 3D, actually, again, you start with the bottommost point first. Okay, from one point, you try to extend it to one line. Now, one line, you extend to a triangle sort of thing. Okay, and from that, you have to start.
Okay.
Okay.
Sir, what was wrong in Lakshmi's approach
Yes.
for finding the first edge?
Uh-huh.
What was incorrect in Lakshmi's approach for finding the first edge? He said that we need to iterate over all points and check if.
So that is also, I'm not saying it is not a correct one. Okay, but you don't need to do all those things. Okay, so we have to find out edge such that all the vertices are one side of that edge, line passing to that edge. Okay.
Okay.
Okay. Now we'll go back to this presentation mode and to this. Yeah, you're able to see this whiteboard, na? Okay. Now, see here, number of edges on this convex hull. In worst case, there can be order n. Suppose if you assume that number of edges on this boundary of this hull, say h, then time complexity becomes order nh. So h can be a maybe some constant, or it can be a order n. In the case of order n, it becomes time complexity order n square. If it is a constant, it becomes a linear. So if you look at this one, the complexity of this algorithm is expressed in terms of a input size as well as output size. So this is what is called a output sensitive algorithm. This gift wrapping algorithm is called a output sensitive algorithm. So you are able to see this one, no?
Sir, could you repeat what is H?
H is the number of edges on the boundary of final output convex hull.
Oh, thank you, sir.
Vertices are edges, both are same. Okay, so we are this is the output size. This is what we output. Okay, H number of vertices or H number of edges in counterclockwise direction or clockwise direction. So the time complexity or NH, so which is expressed in terms of input and output size. That's why this is called output sensitive algorithm. Okay, so now we move on to the next one, what is called a Fickle algorithm. So idea is for the most of the points, okay, we can eliminate large number of points which are definitely inside the convex hull, interior to this convex hull of the given points. So we need to focus only points on the boundary of this convex hull. So for that, what we will do actually, we start with a two vertices on the boundary of the convex hull. So let's take a set of points here. So here I'm taking the leftmost one. Say this is a X and this is Y. Okay, or instead of that, actually we can name them as a point left and point right. Leftmost and rightmost point. So if you look at this line, okay, okay, the leftmost point and rightmost point are certainly lies on the boundary of the convex hull. There's no issue. Now, if you take the line segment passing through these 2 points, then there will be one part of the convex hull above this one, okay, and one part lies below this one. And this is what is called an upper hull and lower hull. Okay, part of the convex hull below this line segment is lower hull, and part of the convex hull above this line segment is upper hull. So you compute the upper hull and lower hull recursively and combine both the solutions, some sort of a divide and conquer strategy. So now we'll discuss how to compute the upper hull. So same method, you can use it for finding the lower hull. Now, so if you want to repeat this step again and next iteration, we have to find at some point which is on the boundary of this convex hull. Okay, say for example, this is one point. Now, if you join these points to this both of PL and PR, okay, so all the points which are inside this triangle are not part of the final convex hull. You can remove them. Now, there could be some points here. Okay, so again we will do this set of points considered for the computing this part of the convex hull here, and these set of points are used to find this part of the convex hull. So this is the recursive way of doing sort of thing. Okay, now only question is how to find out this particular point so that actually we can do this recursively. So here this point can be found many different ways, but one way is you take the topmost point, not a topmost point actually. Of course, in this diagram it looks like a topmost point here. you take the point which is furthest from this line PLPR. So basically you look at all the vertical, perpendicular distance from this line, and whichever is highest perpendicular distance, you take that point. Actually, that is what is a point on the boundary. So this way you can find out this point, and you can do the recursively again. Okay, is that clear? Any questions? So I'm just repeating once again. We are taking the leftmost and rightmost point, and this PL leftmost and PR rightmost points. Okay, you take the line joining them. These two are actually certainly on the boundary of the final convex hull, and this line segment divide the final convex hull into two parts. One is all the points above this define the points, define the upper part of the convex hull, and points below this line segment define the lower part of the convex hull. So we compute these two parts separately, and we match the solutions. So how to find out the upper hull? Now you consider all the points which are above this line PLPR. So there are many are there. So you have to identify one point which is on the upper hull. Okay, so that can be found by considering the by finding the furthest point from the line PLPR. Okay, so furthest point we basically take the perpendicular distance from the each point above this line to this line, and whichever the highest perpendicular distance, we take that point as a point on this one. Okay, so once we did this one, we do the same thing once again for this part. Okay, so you consider all the points here, and one which make the largest perpendicular distance from this line. So you do this one, and you take this triangle. All the points within the triangle is not part of the final convex hull. You can remove it. If there are some points here, you consider them and find this part of the convex hull. If there are some points are here, consider them and find out this part of the convex hull. So you recursively do it for finding the upper hull. The same procedure is followed for lower hull also. Is this clear to everyone? Any questions? See, this algorithm is called a quick hull because this looks very similar to quicksort algorithm, what we discussed, okay, in the algorithms course. So we have a pivot element. With respect to pivot, actually we are sorting we are dividing the points, dividing the values, and we are finding the leftmost and rightmost sorted sequence separately. The same thing here, you have a pivot element. With respect to that, we are dividing the points into two parts, and we are finding the hull for each part. So what is the complexity of this algorithm?
Worst case, n square, big of n square.
Yeah, since it is a quick sort, similar to quick sort, so this partition may be very skewed at each and every level. So in that case, actually, what you will get actually is odd n square. Maybe n minus 1 I kept, maybe okay, other one maybe only 1 point is there, and whole process may take odd n time. Okay, so here this may be 1 or 2 actually doesn't matter. So it's odd n square. So it's exactly similar to the quick sort, the worst case. Now, my question is, can you give an input instance where you will get order n square time complexity here? Can you find out a set of points, okay, where algorithm takes order n square? See, in quick sort, what we used to say actually, if points are already sorted or points are already reverse sorted, then algorithm takes order n square time. Okay. Now, what is the input instance for which this quick hull takes order n square time?
So when all the points are on the convex hull,
Okay.
they are all the vertices of convex
Yeah.
hull.
Okay. Now, what is your name?
Mohit Jain.
Yeah, Mohit given one example where all the points on the boundary of the convex hull, the algorithm takes order n square. Now, I'm asking everybody to verify this fact is correct or not.
So this might not be correct.
Yeah, if it is correct, you have to prove it. If it is not correct, you have to give a counter example. Just give a 1 or 2 minutes to everybody to think of. Okay. Yeah. So you are able to think
So
about this.
we need to impose more conditions. Like the first is all the points are on the convex hull, and that convex hull must have a shape of circle, and all the points are on angle bisectors. So, for example, we have 2 points along the diagonal, and then at 90 degree, then 45 degree, and so on. So that we will have a skewed partition instead of so that's number of iterations.
Okay, so here, yeah, whatever the suggestion mentioned, actually, it's not correct. Because if you take a points on the boundary of a circle, okay, if you are the evenly distributed on this one, and if you take a leftmost and rightmost one, okay, what is happened actually is you off the points on one side, remaining off is another side. Similarly, if you find this point again, and if you divide them, again of the points are one side and of the points are other side. So every time we are getting a balanced partitioning. So in this case, time complexity becomes our n log n. Okay, is not n square. So we get a n square if and only if at every iteration, every level of recursion, okay, only constant points are one side and remaining all points on the other side. Okay, so idea of putting the points on the circle is a good idea, and how to place the points on the circle so that we will get a skewed partition at each and every level. Okay.
Angle bisectors, yeah.
Okay. So if you, why I'm saying the circle is actually, it's a one close approximation of the convex hull. Okay. That's why we are taking the circle. So if you take a circle here, okay. So you start with the 2 points on the diameter, leftmost and rightmost. Now, yeah, maybe we'll take a proper, yeah. Okay, the center may be here. So if you divide the points into two halves, all of them are one side. Suppose if you all are on the one side, on the top. Okay, bottom side nothing is there. Now again, at next level, so suppose if you put a 1 point here, okay, so all the points should be on one side at next level. Obviously, this is actually part of the convex hull. Okay, So all the points should be on side. So you don't keep anything this side. Okay, this time you ruled out and put all the points on this side. Okay, so what you will do next time, actually you put in the middle of this circle here, circular arc here. Okay, so keep on doing like this. So that basically what you're doing actually is you put if you started with this point as a 1, and at 180 degrees you put a second point. If you are okay, and another 90 degrees from here you put third point. Okay, and 45 degrees here and put the fourth point, and 22 and a half 1.8. Yeah, approximately. Actually, this is, you can use any other angle actually. So on next one like this, of course. So this angles actually is need not be like this. Okay, so you have to place points such that actually you will get a partition, skewed partition at each level. If you place like this, you will get it. But these angles actually is not exactly this way. Actually, you can put it any other way also. Okay, this is one way of keeping it. Okay, any questions here? Yeah, we are keeping this actually. This is the highest point or furthest point from the line 1, 2, and this point 4 is the highest furthest from 1, 3, line 1, 3. So that is actually we are using that idea to place this one. So any questions here? So next algorithm is what is called a Graham scan. Graham scan or Graham algorithm, Graham's algorithm. So this is proposed by Grahams. That's why this name is called a Graham scan. And this is the first algorithm whose complexity is okay, n log n. So it is decreasing from the previous order n square to n log n. Okay. So idea here is maybe I am not able to complete it. Okay, let's see. I have to go a little early today. I have some other engagement meeting. Maybe I'll take another 5 minutes and leave it. So suppose if you have points like this, you find any point which is interior to the final convex sun. Okay, and you take a positive x direction. With respect to this positive x direction, you sort all the points angular order. So if you based on the angle made with this one, okay, so basically these angles. So obviously this is the first point sorted sequence, the second, third, and this will be 4, 5, 6. Okay, this is the sorted sequence. So what we'll do, so you will scan through these points in this order and find the convex sun. Okay, now I'll make a small modification to this one. Okay, I will tell you why this has to be like this. I'll take the 2 here. So what I'll do, I'll keep this first point and 2 points for the second point as a part of the convex hull. No, not convex hull. We'll start with this anchor point. And if you look at this one, next one, okay, making a right turn. Yeah, if you walk on this, if you walk along this line in the direction 1, 2, 3, at this point, okay, we are making a left turn. Okay, of course, this point is little away. Okay, let's put this little below. So you are making a slight left turn. So if it is left turn, you consider the 3 also part of the convex hull and move further. Okay, now you look at this 4. Okay, now 2, 3, 4. Okay, when you travel in this direction, you're making a left turn at 3. Okay, proceed. Now you look at this next one, 3, 4, 5. Here also it's making the left turn, 3, 4, 5. Okay, we proceed further. Now look at the 4, 5, 6. If you move in the direction, here you are making the right turn. So when you make the right turn, so this can't be a part of the convex hull, you remove it. Okay. So once you remove this one, okay, now you look at this again, 3, 4, 6. Again, you are making the left turn. Proceed further. Okay, 4, 6, 7, left turn. And 6, 7, 8, left turn. 7, 8, 9, right turn. So this can't be a part of the convex hull. Remove this one. Okay. Now you move one step backward. Now look at the 6, 7, 9. Is a left turn. Proceed. And 7, 9, 10, left turn. Proceed. Okay. Now I'll take another one instead of this 11. Okay. Maybe I'll take a. Okay. I'll stop it here. Okay. Assume the 11 is not there. So we've gone through all of them. Okay. And we completed it. So basically what we're doing. So we are starting from the first point and we're taking the first 2 points in the sorted order. And we are going to next one. If it is that is 1, 2, 3. If it is making left turn, we're proceeding further. If it is not left turn, that we right turn, then we are removing that middle point and we are considering the remaining ones. Okay, like that. Whenever you are left turn, you are moving forward. Whenever you are making right turn, you are removing the middle point and we are moving one step backward and proceeding it actually. So like this, we do it. Okay, finally, what is end up is actually is convex hull. This 1, 2, 3, 4, 6, 7, 9, 10 is the part of the convex hull. Okay, this is what is the proposed by the graph. So now all of you think about this algorithm. Okay, one issue is how to find at a one point which is inside this final convex hull. Okay, and once we have this one, you can sort it, and you can use this sorted sequence to do it. Okay, so when you are moving forward and backward, okay, making left turn, you are moving forward, and right turn, you are moving backward. So this can be implemented using a simple stack. Whenever you move forward, you push it on the stack. Okay, whenever you are considering some point is not done, remove that one from the stack and you do it once again. Okay, so this is what we are doing. Maybe okay, this is what we are doing with this stack. Now this algorithm, what is initially proposed, now this has any issue or not? Okay, you think about it and identify if there are any faults in this one. Okay, and come with this one and we will discuss. Okay, in the next class. So if you look at the complexity wise, so yeah, how to find the internal points is one internal point is one issue. Suppose somehow we found, okay, now sort them all the points angularly with respect to this positive x direction to the internal point, interior point. Okay, you can do it in log n time. Once we have this one sorted sequence, you traverse on this one, scan through these points. So you move forward if it is making left turn. Otherwise, you remove the middle point and come one step backward and keep going. So if you do this one, again, this scan takes a linear time. So overall time complexity is, okay, order n log n, of course. So this is the algorithm what is given in the initially. And if this has any issues, okay, please go through this one and try to find out, and we'll discuss these things in the next class. Okay. So any questions till now?
So the first point might not be in the convex cell every time.
Yeah, that is one issue that I agree. Yes. Anything else is there? Yeah, think about it. Okay, we'll discuss in the next class. Okay. Yeah. So you all of you go through these algorithms. What is there in the book? I am right now looking at the computational geometry in C by Joseph O'Rourke of Oxford University Press. Okay, and soft copy also available actually online. That's what I feel. So you can use that also. At least I know that it's your seniors had this copy. Okay, you can look at that one. Okay, so we'll continue next week. So one thing is we are finalizing the class today. Every week we will meet on Friday also from 12 to 1. Okay, this timetable is final. No, there's no issue.
Yes, sir.
Yeah, nobody reported any issue with this timetable clash. Okay, but exam slot is C, so that you have to take care of the exam slot. They cannot be clash with anything else. That is finalized. Okay, so Wednesday, Thursday, 10 to 11, and Friday is 12 to 1. Okay, I'll fix this schedule in the Teams for every week instead of this thing. Okay, so we'll meet next Wednesday. Okay, see you then.